So we're going to continue our study of kinetics today, and here are our objectives today. Our biggest goal here is to be able to find a rate law, which we'll talk about in a little bit, from data. The last two here, these two really are coming from the reading. I'll do a little bit on catalysis, but mostly from the reading. Okay. So, reaction rate. Let's think about this reaction here. This is the unbalanced combustion of methane. Okay, and let's see, to balance it, we need a 2 here and a 2 here. So, in order for this reaction to happen, there needs to be some collisions, right? So my question is, how could we make this reaction go faster? And I want you to pause and think about it and see what you come up with. All right, so there are a couple things that we can talk about, right? All reactions, you have to have collisions. We talked about collision theory last time. So one of the ways that you could speed up the reaction is you could increase the frequency of the collisions. Another thing that you could do is you could increase the energy of the collisions. So if you increase the energy of the collisions, then you'll get more productive collisions, which will speed up your reaction. And the other thing that you can do is you can decrease the activation energy of the mechanism of the reaction. Okay? Well, how do these things happen? Let's hit the first one first. Increase the frequency of collisions. Okay, well, if you have a solid reacting with something, you could increase the surface area. We talked about this in terms of speeding up the dissolving process. But if you increase the surface area, then there's more, there can be more collisions, and the reaction should happen faster. Another way that you could do this is you could increase the number of particles in a given area. And if this sounds a lot like concentration, then you're paying attention. Yay! All right, so how about increasing energy of the collisions? Well, how do you increase the energy of particles? That one's easy. You increase the temperature. Right? Because remember that the temperature is related to the average kinetic energy of the particles. Decrease activation energy of the reaction. Well, there are two different ways you could do that. You could change the reaction, change reactants. So the identity of the reactants matters in terms of rate. Or you could add a catalyst, and we're going to talk about most of these again. Add a catalyst. All right, so let's look at a couple of these in a little bit more detail. Increasing concentration increases rate. So if I have two particles, A and B, that need to collide with each other, so here's my A side, here's my B side, okay? If I have two particles in this sample area, okay, there's only one possible collision that can occur. Now, okay, let's look at this B here. Instead of just having one possibility, it has two. It can collide with this A, or it could collide with this A. So this increases by a factor of 2, this increases by a factor of 2. So you get 4 possible combinations. So 4 possible combinations for collisions increases the number of collisions. Now we can do something weird, and we can increase the number of possibilities to 6 collisions. And you see that increasing the number of particles in a given area will increase the number of possible collisions that can happen, and that should increase the rate. All right, so this is another way of saying concentration, right? Okay, so that's concentration. What about catalysts? Catalysts are involved in a reaction, but are not consumed. So another way of saying that is you could write them in the reactants and the products. Now, we don't generally do that, all right? If you have a catalyst, let's say here are your reactants, here are your products, we usually write the catalyst over the arrow, okay? But in reality, you could write the catalyst over here on the reactant side and again over here on the product side, because usually they're involved, okay? They might be involved in some of the steps, and they might be like part of an intermediate, but they're going to be freed up again in the end. So they're sort of the opposite of intermediates, right? Intermediates get created and then destroyed, and catalysts might be used and then freed up again later. Okay? And the way that catalysts work is really interesting. So catalysts change the mechanisms. And so by changing the mechanism, you create this sort of alternate pathway. And oftentimes, the alternate pathway will have a lower activation energy. And we talk about two different types of catalysts, heterogeneous catalysts and homogeneous catalysts. So here's a little video that kind of explains the two. Turn things up a little bit.
A homogeneous catalyst is in the same phase as the reactants it acts with. For example, an aqueous solution of potassium iodide can speed up the decomposition of hydrogen peroxide. Heterogeneous catalysts are in a different phase than the materials they are reacting with. Manganese dioxide, a solid catalyst, can also speed up the decomposition of hydrogen peroxide. Different catalysts change the activation energies for a reaction by different amounts.
This is sort of the key diagram about catalysis. You can see that all of the uncatalyzed has the highest activation energy, and the two different catalysts lower the activation barrier depending on how much they're doing.
The potassium iodide lowered the activation energy slightly. Manganese dioxide, on the other hand, lowered it dramatically. Another advantage of manganese dioxide is that, as a heterogeneous catalyst, it is relatively easy to separate from a catalyzed product.
Okay, so that's a little bit about catalysts. Let's go back. So now I want to kind of switch gears and get into like our main thrust for today, and that's rate laws. So the mathematical relationship between the concentrations of reactants and the rate of the reaction is called the rate law. Okay. Rate laws are determined experimentally for each reactant. All right, let's go to an example. Let's consider this reaction. C plus D goes to E. Here I've done some experiments, and notice that I haven't actually done these because this reaction doesn't exist, where I go through and I change the concentration of the two reactants, and I measure the rate. So my question for you is, what is the relationship, mathematical relationship, what is the mathematical relationship between concentration of C and rate and concentration of D and rate? Okay, see if you can figure those things out. So hopefully you paused and thought about that. Let's take, let's answer D first, because D is actually just a little bit easier, okay? If I look at this, okay, D, I want to find two experiments where C doesn't change, but D does. And so that's 1 and 2, all right? If I double the concentration of D, I also double the rate, which to me would say that rate is directly proportional to the concentration of D. All right, that makes sense, right? See if you can figure out the relationship, if you haven't already, between C and rate. Now, this one, I'm going to pick experiment 1 and 3, okay, because I want two experiments where the concentration of D doesn't change, okay? Now this number, we might need to rewrite so that it's in the same power of 10s. This is really 72 times 10 to the minus 8 molar per second. All right. So here the rate has, or the concentration of C has tripled. Okay. And the rate has gone up by a factor of 9. Okay. So by tripling the rate, tripling the concentration, the rate goes up by a factor of 9. So rate is directly proportional to the concentration of C squared, okay? Because C triples, rate goes up by a factor of 9. So I could combine these, right? We've done stuff that looks like this. Rate equals, not equals, sorry, is proportional to concentration of D times the concentration of C squared. And the order doesn't really matter, right? So my question to you is, how do you go from a proportionality to an equality? Think about it. Come up with an answer. You should be able to remember this. Rate equals something times concentration of D times concentration of C squared. In order to go from a proportionality to an equality, you have to add a constant. Now this is going to be another k, lowercase k. And here we go. This is called a rate law. Right? Because if we go back to the last slide, rate law is the mathematical relationship between concentrations of reactants and the rate of the reaction. That's what we have. We have a mathematical relationship between concentration of concentration of reactants and the rate. Okay? Now, we're also, when we describe rate, these relationships, we use something called order. Okay? And order is really just a fancy way of saying power. Okay? So this, I would say that this is first order with respect to D, or in D, right? Because the power of D is really 1. And second order in C, okay? So that's the order with respect to each of the reactants, okay? And then to find the overall order, all you do is you add the powers together, just like you were multiplying them, right? If you were to multiply powers, you just add them together. So it's first order in D, second order in C, so it must be third order overall. Okay? So that is what we, you'll see this term order rather a lot. Okay? Now, this is a rate law. This is a constant. It's a rate constant. And this one, rate constant's actually a little bit tricky. Okay. Where to start? Rate constant, you could get the value pretty easily by plugging in numbers. Okay. So let's actually solve out this rate constant. So K equals rate over concentration of D times concentration of C squared. And I just get that from taking this, my rate law, and dividing both sides by D, concentration of D times concentration of C squared. Okay, because that's, oh, excuse me. I just want to isolate the variable. All right. So if I do that, I have, let's just pick the first one, 8 times, I just pick an experiment and I just plug in the numbers. 8 times 10 to the minus 8 molar per second. And actually, okay, so there's something weird about units. Basically, units equal unhappiness. And I actually think it's cool, but the units of the rate constant depend on the concentration, okay? Because, or the order. Because you know your rate has to be, let's say, molar per second. And these are both in concentration of molar. Uh-oh. So this is in molar, and this is in molar. So if this was, say, first order with respect to C, then that's going to change what the units of the rate constant have to be. And this is second order with respect to C, so that's going to be different units. All right? So when you're figuring out the value of the rate constant, just keep the units out. It's like the one time that I'm kind of okay with just taking the units and separating them. Okay? 1.2 times the concentration of C. Oh, I did that backwards. Yeah, I did that backwards. Concentration of C in the first one is actually 2.4. And the concentration of D is, or concentration of C squared is 1.2 squared. Okay? You plug that in and you'll get your value 2.3 times 10 to the minus 8, okay? And then I have to go back and I have to figure out my units, all right? And maybe it's a good idea to do these a little bit separately. And what I'm going to do is I'm going to do rate over 1 times 1 over concentration of D. I'm just going to kind of FOIL things out a little bit to make it a little bit easier to see. Right? This is the same as this. So rate is going to be in molar per second. Concentration of D is in molar, so that's 1 over molar. And then concentration of C is molar, so that's 1 over molar squared. So one of these molars is going to cancel out. So my units, oh boy, my units are 1 over seconds times molar squared. Okay, so that's kind of a beast. These are fairly long, involved problems, and they take a fair amount of practice, but go slow. And so there are kind of two ways that you can do these. There's some nitty-gritty math, which I will show you in the first sample problem, okay? Or there's the way that we did it here, where we just kind of logic things out, okay? as long as you show me sort of this progression like we did here, then, I that's fine for me.